Alright, so question 23 on page 268. Just gonna go through this real quick. There's a small error here. This should be a 3, but this is indicating half of the base, so imagine that this is just the half and the whole thing is 3. So going forward, the question asks if you have a trough that is 10 feet across, 1.3 feet at the base of the triangle here, and 1 foot deep, then and it's being filled at 12 cubic feet per second, then what is the how fast is it filling up in terms of height? So trough is basically a sort of something you'll find on a farm. It's usually used for holding feed or water. So basically saying if we're pouring water into here and it's filling up this fast, how fast is the water level rising? So, and they also indicate this triangle is an isosceles, and that's important because it helps us get to this formula's meaning. So the ratio between the height and the base is always consistent. So if you have a base of one way, well then the percent relative to the full base that it could be is the same percent for here. So if I had half of this height, I would also have half of this base filled up. So going forward from that, we can say that if we have h here, we'll just replace the one with h. This one isn't full, but if we have h here, then that's the equivalent of saying that regardless of what it is, the ratio will always be the same, and therefore the height of the water, at least on this single part, will also be not necessarily the height, but the width of the triangle will always be 1.5 times whatever the height is. Sorry if that seemed a little disjointed. So going forward from that, we have area of this whole, or the volume, I should say, of this whole trough is given by the width times the height times the half of the base, which is 1.5 h, which will always be the same. And we're actually given a couple of variables. The width is 10, as you can see here. It's being filled 12 cubic feet. And the height is actually 6 inches, or in this situation, it would be read as 0.5, since this is 1 foot, 6 inches half. So, because we have all these variables, we're able to actually go on pretty quickly from there. And here I'm just combining some of the variables. So, take the width of this whole piece, multiply these two parts, we get 1.5 h squared. And from there we can find the derivative. So, you take, because these are all being multiplied, they're not cancelled as if they were added. So you have w plus 3 plus h, w times 3 times h, and then you also have times the derivative of h, since h, how one might figure that out, it might be a formula all in of itself, but derivative of h over the derivative of time, which I didn't write here, but it's implied since everything here has to do with time. So here, just plugging in, bring in the 12, the 10, the 3, and keep the 3 here since it was there to begin with. No, actually it wasn't there to begin with, so I misspoke. So yeah, so the 2 that was brought over when we made the chain rule was turn the 1.5 into a 3. And so you have the 10, the 3, and the 0.5 times the derivative of h, and so it just becomes a matter of multiplying, which you get 12 equals 15 times the derivative of h, which is comes down to a simple matter of dividing 12 by 15, which we get here. So derivative equals 12 over 15, or otherwise known as 4 fifths of a foot every second, and it's only just a foot because it is the two-dimensional measure of actually just one direction going up. So it's the measure of how fast the water level is rising. So that's a one-dimensional measure actually, and so you just have the feet the number of seconds. So that is the end of the problem.